Okay, so good afternoon. Thank you for coming to the seminar. And I'm Tony. I'm one of the stats consultant at Stats Central. And today I'll be talking about latent class analysis and its applications in the medical research. So how many of you have heard about this method, latent class analysis or latent profile analysis? Okay, cool, great, good. So basically, the latent class analysis, the goal of the LCA, like other LCA, the goal of the LCA is to identify the subgroups. So we call the latent classes or the hidden subgroups in a population based on the responses to a set of observed indicators. So so basically, we use latent class analysis to analyze the patterns in the observed variables. And then we, the unobserved, the latent subgroups are statistically inferred from the patterns of the observed indicator variables. And basically, there are two types of the latent class analysis. The one is called the LCA, which is used for the categorical and mainly the binary indicator variables. For example, like the presence or absence of medical condition or symptoms. And the other one is called LPA, latent profile analysis, which is used for the continuous variables, such as the lung function measures or blood pressure or maybe height, weight, the continuous measures. And LCA is actually belongs to a larger family of latent variable techniques called finite mixture models. So basically, the finite mixture models assumes that the study population is made up of a finite number of latent subgroups, and each of these subgroups basically follow its own distribution. Yeah, so instead of fitting one distribution to all the individuals, we combine the multiple distributions and the one distribution for each latent group. So this is what I was talking about. This is an illustration of the latent or hidden subgroups within a population. So we can see that the black solid line is the density of the distribution for the whole population, and the dotted line actually represent the two latent classes. So that's why we have the blue area and we have the red area, right? So the existence, the presence of the latent classes within the population is the central assumption of the latent class analysis. And latent class analysis is a probabilistic method. So that means the latent class analysis does not directly assign individuals to identify the classes, and instead, once the model has been fitted, there's some called posterior probabilities of belonging to the identified class will be estimated for each individual, and we use these probabilities to assign individuals to the class, to the most likely class. So here I've got a very simple example. So basically, after the LCA has been fitted, imagine we have three persons, right? Person 1, 2, and 3. So for person 1, the probability of belonging in the class 1 is 85%. And for class 2 is 15%, for class 3 is 5%. So that's why this person will be assigned to class 1. So the person will be assigned to the most likely class. And why do we need latent class analysis? Actually, the method has been used extensively in psychology over the last 15, 20 years. And over the last 10 years, the method has been introduced to medicine, especially in research medicine research and oncology research. So in medicine, it can help us to identify the homogeneous subgroups within the heterogeneous populations, right? So for example, we may want to identify the phenotypes of asthma because we believe the different phenotypes have distinct clinical and biological features, or maybe some phenotypes are associated with different clinical outcomes, or maybe the phenotypes have differential treatment responses to interventions. So we are interested in the subgroups. Yeah, and this is the differences between the LCA and the traditional clustering method. So the traditional clustering method, such as the k-means or the hierarchical clustering, they use the arbitrary distance measures to group subjects. And also they assign each subject, each patient or each person exclusively to one cluster. And whereas the LCA is model-based, so that means like we can evaluate how well the model fits the data, right? And also the LCA give us the class member probabilities for each subject, and also it gives us the other model fit statistics such as the AIC, BIC, and the entropy. I'll talk about those model fit indices later. And also, like moreover, the LCA has got some other advantages over the traditional method. For example, the LCA can handle different types of the indicator variables, or even like the different scalings. Whereas the traditional method can normally like they are limited to like to a numeric or only a single data type, and the LCA can also like better handle missing data. So there is like there was a very famous simulation study back in 2002, and so the researchers studied the accuracy of the LCA and the k-means clustering in correctly identifying the classes where the true class membership was known but was concealed during analysis, and they found that the misclassification rate was 4 times higher using the traditional method compared to the LCA. And now I would like to show some like the examples of the application of LCA in medical research. For example, this one is a retrospective cohort study. So they used the LCA to identify the comorbidity profiles in 6,000 patients with lung cancer, like in California states. And LCA actually identified 5 distinct comorbidity classes. And the classes were defined by progressively greater CCI score, and also was defined by the presence or absence of the specific type of vascular disease and diabetes. And most importantly, they found that the comorbidity class was independently associated with treatment selection and survival, especially among patients with the early stage of lung cancer. So this is pretty important. This one is another study using the LCA. It's from Melbourne, Australia. It's a very good study. So it's a prospective cohort study. Used the LCA to identify the trajectories or the profiles of asthma and allergy from age 7 to age 53 in the Tasmanian cohort. And they identified 5 asthma and allergy trajectories over the ages. And also, most importantly, we found that the COPD, which is the chronic obstructive pulmonary disease, was most strongly associated with the worst trajectory. So those 2 examples are LCA latent class analysis because they use the binary indicator variables. And this example is latent profile analysis. Actually, is like one of the studies from my PhD. So I used the latent profile analysis to identify the trajectories of lung function from age 9 to age 45 years in the Dunedin study cohort in New Zealand. So the study identified the 10 distinct FEV1 trajectories. So FEV1 is one of the most important lung function parameters, right? So let me show some results. So basically, like those lines, 10 trajectories, are the trajectories I found using the latent profile analysis. So we can see that, I mean, the x-axis we have age from age 9 to age 45. And the y-axis, we have the lung function, like the percentage predicted FEV1. So basically, we can see that most of the trajectories are sort of approximately parallel. So that means lung function tracks from age 9 to age 45 years. So that means like, in other words, like that means for most of the people, their lung function trajectory up to age 45 are actually largely established before age 9. But there are some exceptions. One exception is the bottom trajectory, namely like the persistent low trajectory, 3% of the population. So that is like that one started very low and then like diverged across ages, right? So that trajectory is associated with severe childhood asthma and hyperresponsiveness. And also the other 2 exceptions are the 2 accelerated decline trajectories. So we have the pink line and the purple line. So they are the accelerated lung function decline trajectories. They are associated with obesity and smoking. And also, I found that the bottom three trajectories, the worst three, they comprised 19% of the cohort, but contributed more than half of the CVP at age 45 years. And now, like, I want to just go through the key steps in LCA, and I think these steps are very important. So, like for example, just briefly, like in step one, once you have the data, right, you have the study population. I think in step one, like you need to carefully choose your indicator variables. And in step two, before you do the analysis, you need to check the data properly. And in step three, like we fit the LCA model or LPA model. We normally just fit like a series model with increasing number of classes. And in step four, we evaluate all the models and we pick the best or the optimal model. And so step five, we do the interpretation, and occasionally, sometimes we need to do some external validation as well. So step one is after like so I'm going to go through these steps one by one, and then I'll show some like examples in STAT and in R. So step one is the indicator variable selection. So this is very important actually. This is the key decision that shapes your latent classes identified. So you need to think about like what variables you're going to put in the LCA model, and like the inclusion of any variables should be guided by a very clear rationale. And this selection should be based on your research question and based on your clinical knowledge. So for example, if like in psychology, people normally use like the symptoms of depression or anxiety. And in medicine, people normally use like the absence of a disease or a medical condition. And for public health, people may use like the binary indicator for smoking, alcohol use, physical activity, etc., etc. And there, I would like to like present two special cases. The special case one is something to do with the summary score. So in critical care medicine research, sometimes like the people want to use the summary severity score, such as the SOFA. SOFA is the sequential organ failure assessment. Yeah, I think so. So they want to put the summary severity score in their LCA model. Actually, it's not right. So because for the summary severity score such as SOFA, a lot of the time its components already part of the LCA model. So that means like they are trying to put like both the summary score and its components in the LCA model at the same time. It's not right. We shouldn't do this. I mean, we should you can only include the summary score or its components. And the best practice is to use the individual components rather than the summary score. And another special case is that sometimes like the researchers want to put the clinical outcomes as the indicators, and this is not right. Because including the outcomes as class-defined indicator variables will bias the classroom, right? And also that will introduce something called circularity. So basically, like the right approach, the logical approach is that you fit your LCA model using the carefully chosen selected variables, right? And then once the classes are identified, you can study associations, for example, between the identified classes and the health outcomes. But you cannot use the outcome as the indicator variable, right? Because like if the outcomes are used to define the classes, then like the later you want to of course you will see the difference in these outcomes between the classes, right? Then this is nonsense. And step two is the data setup. So once all the variables, like the indicator variables are chosen, before you do the analysis, you need to do the data checkup, right? And you need to check for the extreme values, right? Because the LCA models can be sensitive to the extreme values. And also, normally for continuous variables, you need to examine the univariate distribution for each of the indicator variables. And if needed, you need to do some sort of transformation, right? I mean, it's arbitrary to use, the type of transformation, maybe log transformation, maybe square root, it doesn't matter. And for categorical variables, like you need to examine the frequencies, the category frequencies, right? And sometimes if the categories, if you have like categories with very low frequencies, say less than 10% or 5%, you may need to collapse or combine the categories. And sometimes you have like indicator variables with different, different like they're measured on different range of scales. And in theory, the LCA model can accommodate variables with different scales, but in practice, the model fitting may become difficult. So maybe you need to do some sort of like the standardization, like such as Z-score. And what is the required, like the minimum required sample size for the LCA? Actually, we don't know. I mean, like at least to date, like there's like no guideline for the minimum sample size required for the LCA. But according to the results from some simulation studies, like in summary, LCA can be considered as a large sample method. So what simulation study found that when the sample size is greater than 300, I mean, the models like considering performs very high accuracy. So when the sample size is less than 300, the results may be, less reliable. And when the sample size is less than 100, like I think it's still possible to perform the LCA, but we'll do the interpretation. You're gonna the results needs to be interpreted with caution. Because if the sample size is like the inadequate, small sample size may lead to convergence issues. Like you don't have insufficient power to detect the classes, right? Or like the solutions will become very, very unstable. And for the missing data, basically like there are like three options, right? So option one is deletion, which is like I don't recommend you just deleting the observations, right? And you can use like either multiple imputation or something called full information maximum likelihood. And so the FIML thing does not impute the data. Actually, it uses all the data, both complete and incomplete. It is available in most software packages that are used for the LCA. So, but sometimes it may take quite a long time to finish the calculation. So in step 3, so once the indicator variables are selected and the data has been properly checked, you can start fitting the model. So normally, like we start with a one-class LCA model, which serves as the baseline, and then each time we increase the number of classes by 1, and we check if the additional class improves the model fit. And we usually stop fitting additional classes when like A, like the model is over parameterized. And B, like you have like encountered the convergence issues, right? So these two things are often flagged by the error message in the software. And once all the models are fitted, basically we collect the model fit statistics from each model, and we normally summarize them in a single table for evaluation. And the number of models to fit is largely determined by your sample size, by the number and the quality of your indicators, and also by the minimum acceptable size of your smallest class. Oh yeah, this is maybe the most important slide of this seminar. So model selection. So I mean, yes. So in practice, to select the best or the optimal LCA models, you need to consider these 4 things. So you need to look at the model fit indices, right, such as the ASE and the BSE. And there's another thing called sample size adjusted BSE. Basically, for those information criteria, the lower the value, the better the model fit. And then you need to check something called entropy, which is a measure of the class separation. So basically, the higher the entropy, the better the model fit. I mean, the higher the entropy, I mean, the cleaner the separations. And also, you need to check the class sizes because you don't want to get a very small data sizes, right? And also, the most importantly, you need to think about the clinical relevance and the utility of identified classes. I mean, all the classes need to be meaningful, right? Like from either a clinical or biological point of view, or maybe from both. Right. So you use these 4 criteria to select your best model. And sometimes like you realize, for example, if you have a very large data set, right? So as you increase the number of classes, I mean the BSE keeps going down. So basically, like you will end up with a very complicated models, right? So in that case, you can do something called elbow plot. Basically, you can plot the BSE. So here is a very simple example of the elbow plot. So on x-axis, we have the number of classes, right, from 1 class to 5 class. On the y-axis, you have the BSE. So basically, we want to plot the BSE, and we look for something called the plateau point. So the red arrow indicates the plateau point here. So the plateau point means, like from the plateau point onwards, the further increases in the model complexity, like the further increases in the number of classes in the model, does not give us the same decrease in the BSE. So maybe the class model is probably like the best model in this case, in this very oversimplified case. And in step 5, we do the interpretations. Yes, normally, and in practice, normally we use the probability cutoff of 0.5 to assign class. And in theory, if the model fits the data well and entropy is high enough, the posterior probabilities should be close to 1 for one class and should be close to 0 for the other classes, right? So the information loss from this classify analyze approach is minimal in theory. And also, like occasionally, if you have if the data is available, you may also want to do some external validations, right? Because if we can replicate the findings in the primary analysis using the same set of indicator variables in the second independent population, and that would greatly increase the generalizability of the findings, right? And like there are 2 questions to address in the external validation. Okay, so now we can look at some like the examples. So how to perform LCA in starter? So this example is called like the teenager behavior problems, teenager behavior examples. So imagine we have a set of 5 binary indicator variables that indicate whether the adolescents have consumed alcohol, have more than 10 unexcused absence from the school, have used a weapon in a fight, have engaged in vandalism, and have stolen objects, right? So basically here, like we are fitting a latent class model with 3 latent classes using the GSAM function. So the GSAM stands for the generalized structure equation models. And instead, we use the GSAM, like both the LCA and LPA are under the GSAM framework. And yes, and the log is because like those indicator variables are binary, so like the log we just log it for the link function, right? So basically now, like instead after we fit model, we can use the estat LC prop to give us the proportions of the classes. So we can see that like we have identified 3 classes, right? And approximately 16% of the teenagers are in class 1, 80% in class 2, and 4% in class 3. And also, like after we fit the model, we can use the estat LC min to give us to estimate like the min for each item in each class. So like how do we interpret these results? If we look at the first class, so it means that for the teenagers in class 1, on average, I mean the probability of using alcohol is 75%. And similarly, like the probability of involved in the vandalism is 24%. That's the interpretation. No, we cannot perform LC in SPSS. No, we cannot. I mean, SPSS does not support LCA. And normally, like we can summarize the results in a single table, right? So basically, we can tell that according to those 5 indicator variables, we know that like class 2 is the teenagers in class 2 are the well-behaved ones, and those ones in the class 3 are the worst behaved ones. And class 1 is generally okay, but maybe they have some problem with alcohol use and being truant, right? And also, okay, yes. So if the indicator variables are ordinal, we can just like update the code a little bit by changing the link function from logit to logit to logit. And actually, in starter, with the gsum function, we can this is the example below. So in starter, actually, we can customize the distribution for each indicator variables. So in this example, we still have the 5 indicator variables, right? But the alcohol is continuous, and the truant is a count variable, and we also have 2 binary variables, the weapon and vandalism, and the theft is ordinal variables. We can customize the distribution for each variable, which gives us the flexibility. And how do we perform LCA-R? The several packages can be used. For example, the PO-LCA, the random LCA, and the tidy SEM. So the PO-LCA is the most commonly used one. It's very popular. So basically, imagine we have a data frame of 180 observations, biopsies, and we have 7 variables. Each variable is a rating from a pathologist on the presence of a medical condition or a disease, right? So to run LCA, we load the PO-LCA package. We load data, and then here we are fitting 3 LCA models, right, with the 2 class, 3 class, and the 4 classes. This is yes, and I mean for the 4 class model, we can to help the model converge, we can increase the for example, the number of estimations, or we can also increase the number of iterations. That's why we have the arguments model. And how do we fit LPA in starter? The LPA is the latent profile analysis, the one used for the continuous variable. So imagine if we want to identify, this from my PhD. If we want to identify the trajectories of long function, right? We can use LPA. So here, we are still using the gsum function, but now we have 10 continuous variables. Right? So those are the long function parameters from age 9 to age 45 years, and we are fitting a latent profile analysis model with 4 latent classes. And these are the estimated mean for each item in each class. So now the interpretation is that, for example, for the study members in class 1, on average, the percentage predicted long function at age 9 is 98%. That's the way we interpret the data. Yeah, these are the results for class 3 and 4. Okay. So this is how we how we just want to show an example of the for example, after the LPA model has been fitted, and we can calculate the posterior probabilities, right? So for example, if we look at the table on the right, for example, for the study member 201, the chance of belonging to class 1 is 93%, right? So this person will be assigned to class 1, and it's similarly the next study number 202 will be assigned to class 1, and for study number 203, the chance of belonging to class 4 is nearly 100%, right? So the person will be assigned to class 4. For the observation number 5, study member 206, actually the probability of belonging to class 2 is 43%, and the probability of belonging to class 4 is 56%. So this person will be assigned to class 4, something like that. So the person will be assigned to the most likely class. But I mean, if we compare the the observation 5 to observation 1, I mean, that separation for observation 5 is not as clean as the separation for the observation number 1. This is like how we like store the model fit statistics and also summarize them in a single table, right? So basically here, like we just run the 4 class, 5 class, 6 class model, and we store the ASE and the BSE, and then we just present them in a single table, right? So this will help us to to do the model evaluation. And how do we perform LPA in R? So basically, like the people use these two packages, tidy LPA or mclast. So this is pretty straightforward. So here, we load the package tidy LPA first, and then we use the estimate underscore profile function to fit a series of LPA model from 1 class to 6 class, right? Limitations. So although like the latent class analysis is very powerful, but just like any other method, it has some limitations. So for example, the LCA generally is a large sample method. So that means like in order to perform a high quality LCA, you're going to have like a decent sample size. And also for LCA, like the model selection sometimes is quite difficult to choose the optimal model, right? And also there's another thing called naming fallacy. So it means like after the classes are identified, and researchers normally need to assign names to these classes, right? But sometimes this can be because like the classes can be complex. So maybe sometimes the chosen label may oversimplify or misrepresent the actual class characteristics. And these are the key take-home messages. So basically, the LCA and LPA is a method that allow us to identify the latent subgroups in the population, right, based on the responses to the set of indicated variables, and also please follow the key steps, and also to do a decent model selection. You need to look at the model fit indices, entropy, your class size, and also most importantly, the clean relevance of the identified classes. Yeah, this is just like a list of references. You can have a read if you're interested. I mean, the top 3 are the methodology papers, the other 3 are the applications. Okay, thank you. Hi, Paris. We can. I don't like in SPSS. We cannot do the LCA. I think you can do something called this 2-step clustering analysis. It doesn't support the LCA or LPA.
Thanks so much.
Yeah.
Why doesn't it go back up? Why does it just keep going down?
It will keep going down as the number of classes, absolutely, as long the number of classes. Oh yeah, sometimes I would like to mention one extreme situation. Sometimes, for example, if you have the data right and you fit the LCA model, you fit the 1 class model to 8 class model, and when you do the model evaluation, it shows that the 1 class model has the lowest BSE. So this happens rarely, but I've seen this happen before. So that means there are 2 plausible explanations. The first is that maybe you believe the latent classes exist, but actually they do not exist in this population. So this is the ground truth. And maybe another explanation is that these latent classes actually exist, but you just don't have the, you just like, for some reason you didn't detect them. Maybe because like the indicator variables you used for the model, they don't have good quality, or they don't have a good like differentiating ability. So that means maybe you need to consider using another set of indicator variables. That may give you the result you want. And also, please, like if you want to do the LCA, please don't skip the step 1 and step 2, because like over the years I've seen researchers, they just skip the step 1, step 2. They start with the step 3. They just like start fitting the model straight away without thinking about it. I mean, whether like what sort of the indicator variables they should use to answer the research question, or without properly checking the data. So that means I've seen like after 3 months everything has been done, the paper has been drafted, but they need to redo the whole thing because like the results are basically rubbish.
Are there any underlying assumptions on like, do the continuous variables need to be normal or anything like that?
Not really. I think the assumption, like the key assumption is that I think there are 2 key assumptions behind the LCA. One assumption is that like the latent or hidden classes actually exist in this population, and another assumption is that within each latent class, like the indicator variable should be like reasonably independent from each other. But I mean, for LCA, there is no formal statistical testing. So that's why you need to carefully choose indicator variables. And also, you need to make, after the classes are identified, you need to sort of like make sense of the classes by, for example, studying association between the classes and your outcome of interest to see if like the results are expected. But there's like no formal testing for the subjects. And also, I've heard like this is pretty random. Like a month ago, I've heard like there's a new method. Nowadays there's a thing called latent class survival model. So basically, you can combine the latent class analysis with the Cox model. So basically, you can identify the subgroups in the population, and at the same time, you can estimating the time to event outcomes. This is something pretty new. Yes.
For small sample sizes,
Yeah.
is the likely outcome that you just won't find anything, or that it's just contrast?
If you have like small sample size, I've seen people like did LCA with 60 patients. So I think they still identified 3 classes. Yes, but you're gonna be, when you do interpretation, you're gonna be very careful. You're gonna mention the listen limitation. Like it's still possible, but you need to have a good paragraph to explain this in the discussion. Yeah. And sometimes I think I think yes. Yes, I think you can use, I'm pretty sure you can use the latent, you can use SAS to do the analysis. I'm pretty sure like you can do either the LC or LPA, but I haven't done it myself. But Nancy can.
Well, you definitely can use
Structured vision model.
Group-based trajectory
Yeah,
modeling, which allows multiple outcomes, figures of membership and classes, and also analysis of subsequent outcomes from predicted groups.
Yeah.
I don't know if anybody heard that. You might want to.
Oh. Yes, hi, Lara. Yes, yes, you can use you can definitely use SAS for the latent class analysis.
Thank you. I heard the answer.
Oh, okay, cool, great.
The procedure is called PROC-TRAJ, T-R-A-J.
Sorry, PROC, which one?
TRAJ, T-R-A-J, TRAJ for trajectory.
Perfect. Thank you.
Oh, really? Look. Chat. Oh, I mean, if like, for example, like for you, if you are fitting LCA and the model doesn't converge, that means like you need to do something like, for example, you need to reduce the number of classes, or you need to like reduce the number of the indicated variables. You need to do something, or otherwise you can just like the example I showed you can maximize the number of estimations or maximize the number of iterations. Just try to help the model to converge. Very difficult task. Oh, it's high next. Yes, I agree. Yes, yes. Yep. Sure. Yes. Oh, yeah, thank you. Very quick. Latent class trace model. Do they have similar features used today? Mari, to your question, to be honest, I don't have the answer with me now. I haven't done the latent class trace model, but I can find out and get back to you. And also like the one thing to mention, the LCA, the latent class analysis can be used for like either cross-sectional or longitudinal data. So you can, it's pretty flexible. And yeah, another thing to mention, of course, so please do not use the demographics variables such as age or sex as the indicator variables. Yeah, it doesn't make any sense. You can still you can still like fit them in the model as a covariate, but they cannot be used as the indicator variables.
That's it. So it's,
Yeah, sure. How do you measure the person? Make sure. So let me just find it. So the question is like how do I mean, how do we know that a particular person belongs to a particular class, right? Not to a particular class. I think so that's why like we always like, for example, we always when we look at the posterior probabilities, right? We always want to see something like, there's no cutoff, but people use like 80% or 85%. So if the probability for a person to belong a particular class is greater than 80%, like this is pretty, acceptable. But there's always like a bit of uncertainty. So always wants to see the very high probabilities, right? I think we will never be sure like what is the truth, right? We just want to, I mean, if we just follow those key steps, we should be able to get something decent. Okay. Should I stop? Oh.
So thanks, Danny, for your talk. That's what I'd like to do, and hopefully we'll see you guys next time as well.